that the study guides have, but we can go through it if
Oh,
you want.
really? So, oh, there are mistakes in the study guide.
Yes, there's mistakes in the study guide. There's like some mistakes in the study guide, like
Oh,
some.
okay.
Cool, man. Okay,
That's yeah, that's not good. Okay, so now let me just find the PDF. This time, what I'm going to try and do is actually share a link to the whiteboard and see if you guys can actually access it. So just give me a second. This is the whiteboard, and then I should be able to share a link here. Send email. Oh, there we go. What's this? Income, rights to search. Okay, invite others. Create sharing link. There we go. Copy link. And then I'm gonna go to the WhatsApp chat very quickly, and I'm gonna paste this. So if you have your laptop at home, so here we go. Whiteboard link. Okay, cool. So let's talk about the differentiation, right? If you look at the a basic summary of this chapter is that we have this concept of differentiation, which is concerned with derivatives, right? And if you don't understand a derivative, then you won't understand this whole section of on differentiation. So differentiation deals with the rate at which a mathematical function is increasing or decreasing, right? Over a series, and there are five main rules that we have to be aware of when we're dealing with differentiation, right? There's obviously the power rule, and then there's the rules around exponential and logarithmic functions, and then we have the chain rule, then we have the product rule, and then there's the quotient rule, right? So let's go to the beginning of the chapter and then discuss differentiation. Cool. So can anybody actually tell me what this triangle here is called? Samagwini, do you know what this triangle is called?
Change.
Change. No, it's actually it is change, right?
Yeah.
It is change, but the technical term for that this triangle is delta, and it turns out that this is the fourth letter in the Greek alphabet, right? So we have alpha, beta, gamma, and delta.
Yeah. No. Okay.
And delta, what delta is concerned with is vertical change over horizontal change, right? And because we are dealing with a line, yeah, because we've been dealing with straight lines so far up until chapter 3, the slope the slope of the line over a series was always constant, right? However, for these curves that are being introduced as we start dealing with exponential functions and polynomials, that slope is different at different points, right? So all that we are dealing with when we are talking about this concept of tangent again is a straight line that touches a curve. That's all a tangent is. And this obviously the straight line that touches a curve at a certain point can also be thought of as the yeah as a tangent, and it represents the slope at that specific point. So they kind of like go into detail here with this chords example. Do you want me to just run through this in more detail? Because if you don't understand this what's actually going on here,
Yeah.
should I do a bit of a deep dive into this?
Yeah. Please.
Oh, okay. Uh,
I think that's where I really do not understand. I can get others. I get the graphing of it is where I'm confused.
Oh, okay. I mean, this took me about 3 months to understand, so I completely get you. So I was pretty bad at drawing lines in our last session, so I have a little trick now. You actually put a ruler on my tablet, like a physical ruler on my tablet. Let's see if this works. And you quickly, yeah, okay. So it's not picking up. Oh, there we go. So now let's choose black. Cool. So I'm just gonna draw a. Okay, I need this thing to behave. So here we go. There we go. That's more straight than before. Just give me a second, and then I'll. It's another straight line. Okay, so let's say we have a what they're saying here. Okay, I'm gonna rub out all this other nonsense here, and just need to find the rubber. Cool. And just delete that. Delete all this other garbage here. Delete. Delete. Okay, cool. So here we go. Here's our graph, right? And let's say this graph is a we're dealing with y equals fx, whatever form that might take. And let's say in this specific example, we have a graph in that takes this kind of shape, right? So we have an upside down u. We might have an upside down u like that, right? And then we plot 3 points on this graph, right? So we have a point there, and then we have a point there, and then we have a point here. And we call these points, point A, and then we have point B here, and then we have point C. So what they're saying here, okay, cool. So the first sort of term you have to understand here, and just please just imagine that this these are all connecting, and this is zero, and this is a vertical line that's just straight. So what they're saying here is if you get a straight line, and I'm gonna draw a straight line connecting point A and B. So if you draw a straight line connecting point A and B, and then draw another straight line connecting A and B and C, not A and C. God, I've got the A and C on my mind. We're gonna be voting tomorrow. Cool.
Yeah, man. It's voting day tomorrow.
Yeah. Oh, Monday, right? So what they're saying here
It's Monday.
is this. If you draw a straight line on this f equals fx, right? So if we call this graph f, this graph fx. I'm not going to go into detail as to what the function actually is, but if you draw a line that connects these 2 points, that's a straight line. That line is referred to as a chord, right? So that's the first term that is introduced in this chapter that was new to me, right? And you have to understand what a chord is first,
Okay.
because the nature of these chords is what we use to actually figure out what the derivatives of these functions are, right? So if you draw a chord from A to B, what's happening here? If you look at the behavior of this chord, how would you describe the chord, Tamaguini?
It's decline. It's what's going down. What is it? Negative? Declining. This is. I don't know.
Yeah, yeah, it's steep. It's quite steep.
Yeah.
Okay, cool. And then in the example, they also have point D. Sorry, that I forgot to mention.
Decreasing. Why did I say declining? Decreasing.
Yes, it is. Yeah, declining and decreasing is the same thing, right? So here's another chord here that's quite steep. So this is a point D here, and then we have another. Okay, cool. So this over here, we have. If we are to describe this behavior, then we can say that between point A and B, we have a situation where the chord is steep and it's negative, right? And then between point B and C, what's happening here, right? We have a situation where it's kind of it's increasing, but it isn't as steep as chord AB. And then between point C and D, we have a positive slope again, but it's much steeper. So understanding that is very important, right? So what they're doing in the example is that they're saying that we can actually progressively decrease points. We can create like a subset of points, right, between point B and C, right? And what they've done in the textbooks is that they've created another point here between these two. They've created two additional points here, and they're calling this point, this like C star, and then this is C star star, which is like C2, right?
Okay.
And then again, we dealt with delta earlier, which is vertical change and horizontal change. And what they're saying here is that if we progressively shorten point BC, so that delta x gets smaller and smaller, right? So this is obviously delta x. This is the x-axis, and we're dealing with change over x here. So let's then draw out delta x, new chords that represent these new c's, right? So just imagine that this is a straight line and this is also a straight line. So what's happening here is the change in x is getting smaller and smaller. Delta x is getting smaller and smaller. So if we added a third c here, what the behavior could be described as, you know, delta x is tending towards zero, right? So delta x might be we might only change 5 points here, and then we might only change 4 points here, and then 3 points here. So delta x can be described as tending towards zero. Delta x can be described as tending towards zero. So Tomaguni, is that clear? And then another way of representing the fact that delta x, if we uh, progressively kind of like plot these curves, another way of describing this behavior is that, you know, delta x, so delta x, 0, and then you put a limit here. So this delta x here that we are dealing with here, or delta y over x, if we are trying to represent the the curve of this line, we are dealing with altogether, right? And not just delta x. If we're trying to represent the curve of this line as it's changing, remember we spoke about delta earlier. We can represent that curve as, you know, this delta y over delta x, or change in the y coordinates minus change in the x coordinates, right? So this is obviously that y2 minus y1, and then over here we have x2 minus x1, right? And again, the important thing to note here is that delta x is getting smaller and smaller and smaller. So the derivative of this function, right, which is sometimes called the slope of the curve of a function, or the rate of which this function is changing, is this delta y over delta x. So again, we have this term, the derivative, and then we have the term, the tangent, and we have another term to describe this delta, vertical change over horizontal change. Right? All these things mean the same thing. So we are, remember again, a tangent is the slope of a curve at any specific point. So then, if we are interested in representing, in saying that the derivative of this function, which is which is a function, which is basically a model that represents how this curve is accelerating or decreasing at a specific point, how this chord is accelerating at a different point, is just this. And we can then express that using a new notation that we haven't used before, which is this function, the original function, with a little 1 here. And then if we were to complete this whole set of rule, you can say that the derivative of the original function, right? So if we had an original function, let's say the original function was just fx, and then we were interested in how the tangent of fx at a specific point between 2 points, we can then say that the derivative of fx, so this is fx and fx are not equal. So if we have fx, and again, like maths is actually more about language and learning how to express things and model things, right? So we say here, if we have fx, then the derivative of fx, so the derivative, or we can say the derivative, again, it's the same thing, it's all the same thing, the derivative of xx, or we can say the tangent of xx, right? Or we can say, the rate of change of fx, change. Or what else? What else is the? So we have derivatives. We can express it with this notation here, or we can say the tangent of fx, or we can say the rate of change of fx, or what else? How else can we express the derivative? We can say, the slope of a chord between 2 points. So the slope of a chord between points. Actually, you don't have to say between points, because when we say a chord, we can assume that we are dealing with 2 points on the graph. But all that a derivative is an expression, is a way of describing how is a way of describing the chord, right? As I said earlier, we have this chord between a and b, and here we have for our function between these 2 points, x, this is x1 and this might be x2, the chord can be said to be decreasing with a steep slope. And then over here, it's positive with a slightly uh, with a less steep slope. And then here it's very steep and it's very positive, right? So the chord, or the slope of the chord, is the derivative of that function over 2 points. So Tomagwini, is that clear that we're talking about the same thing here, but we're just using different languages?
Yeah.
Okay, cool. So now let's talk about the differentiation rules. Yeah, again, what I just want to emphasize here is differentiation is the process of finding the derivative of y with respect to x, or the change of y over x, right? And we do this using some rules, right? And when we're talking about derivatives as well, we're talking about general functions, right? We are basically trying to model the way a function behaves. So we might not know what the values of the constants are. So it isn't like we're adding, 1 + 1 = 2. We're dealing with constant variables that we might not know, and we have generalized sort of abstractions of a mathematical function like fx, and we're trying to understand how these abstract functions that represents a model for the behavior of data might be increasing or decreasing, right? So there are four rules for differentiating a function, right? So I'm going to say here differentiate. Cool. So does anybody here want to take is anybody here feeling brave and wants to explain what the rules are, or who wants to maybe take a gamble at explaining one of the rules, and then I'll do the others. I mean, okay, fine. Let me do this, right? I'll do the power rule, I'll do the exponential and natural logarithmic functions rule, and I'll do the chain rule. And then hopefully by that time, we haven't gotten to 8 o'clock at that time, and then maybe Kamagwini or Gift, you guys can do the product rule and the quotient rule. Anyway, so, and really, I'm gonna do this just for the sake of some of you who might be screenshotting. Okay, cool. So we have these differential rules, and there's only five of them. I know it's a lot of pages in the textbook, but there are only five of them. And then three. Okay, I'm gonna put the three here. And then the fourth one we can put here because I'm gonna write the rules. I'm just gonna write the rules down. Did you guys allow that person in? Sorry. Gift or Notando, can you guys just admit these people who are waiting
I did.
outside in the lobby? Okay, cool. Because I'm yeah, it's on a different screen. Okay, cool.
Don't worry. I'll just allow them. I'll just admit people.
Okay, cool.
I'll
So
be the interest person.
you be the bouncer. Make sure those scammers who are selling study guides in the WhatsApp group do not get in. Thank you. Okay, so we have the power rule, which is I think maybe it's the first one that's introduced in the textbook, but I actually think it's one of the more complicated one because the power rule within it we have three sub rules within the power rule, and then we have sort of the exponential and natural logarithmic rules. Cool. And then we also have the chain rule here. And then we have the product rule. So I'm going to say here product rule. And then we have the quotient rules, right? So if you can just memorize this little spider diagram, like write it out in your little notes that you're taking, I'm sure you'll dominate in the section. Because the next section, chapter 6, all that we are doing really is applying these to real world scenarios. And this graph, once we've done scoping it out, will be the summary of the whole chapter, right? So let's talk about the power rule. Just going to find. So we've just spoken about all of this here, blah, 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 blah. The limit as x tends to 0 because the chord is getting smaller between b and c. That can be described as the derivative of the function. So let's talk about the power rule for differentiation. Just give me a second. Here we go. There was no lights here. So the basic rule to determine this other function that describes how how a basic hyperbola might behave is the following rule. So if we have for the power rule, right? So if we have let's talk about the power rule. Power rule. So if we have a function that's expressed by the following, right? Y equals fx. Y equals x to the power of n. To the power of n. Or you can also express this as fx equals x over n. Right? So this is the same thing, x to the power of n, right? Then, so if we're trying to express that chord or describe how this function y equals x to the power of n, which is sort of which is not an exponential function because with an exponential function x is the power, not the n. Here n is the constant that's changing, right? So if we were to differentiate this, which is to say, if we were to describe how this function is changing, we use the following rule, right? So we say the derivative, which is how this graph changes over time, the vertical, equals n times x to the power of, right? You guys remember this? N minus 1. And then they include some examples here in the textbook as well. So if we had a function that was given to us, let's say y equals, I'm going to put here example. So if you have a function that was given to us here, let's say y equals x to the power of 5, like that, then a mathematical model that describes how this function might be behaving over time can be expressed by the following function, right? We have the derivative, we can say, or so another way of saying a mathematical formula that describes how this function is behaving over time is the derivative. We say the derivative of this function equals, according to the power rule, remember, equals 5. Because remember, 5 was what is. So we're taking that exponent and we are bringing it. We are making it. Yeah, we bring it to the front. Equals 5x minus to the power of this 5 minus 1, which is obviously then 5x to the power of 4. Cool. But there are now some additional rules that we must consider when we are using the power rule, right? And these rules are the following, right? When a mathematical term is divided or multiplied by a constant, you can differentiate the term itself and then multiply or divide by the constant. Does anybody, do you all understand what that means? Which is to say, so now let's go into those three rules and what they might mean. I'm gonna just try and make this bold. No, it doesn't go bold. Okay. So now there's three rules here, and I want to put this as rule number one, power rule. I'm gonna call this power rule sub rule note one. Note one. And I can see why people who are native English speakers might struggle with this module, because this language, this English, is actually quite advanced. But all that they are saying here is that when a math term is divided or multiplied by a constant, you can differentiate the term itself and then multiply or divide by the constant. So now this is obviously a lot of words. When you can differentiate the term itself and then multiply and divide by the constant. So now a mathematical an abstraction of all of this text, right, is the following a mathematical function, right? You can say, so if you have the original function is something like k, a constant, right, times x to the power of n. You don't have to differentiate all of this together. You can actually, so this is the term that you're interested in differentiating here. It's not k times x to the power of n. You can actually differentiate this term on its own and then times by k later, right? So the derivative or the change or derivative,
Okay.
the derivative can be expressed as following. You say k times the derivative, right? Derivative delta y over delta x of the original function, right? X to the power of n, which gives you k times, obviously according to the power rule, this would be, sorry, times, this would be what is it, n x to the power of n minus 1. It's the same thing. And the important thing here to remember as well, okay, so I'm gonna do it. a practical example before I expand on some notes on this thing here. So then, if we go back to the textbook, and I'm not going to write this down. I'll just take a screenshot. The power rule for differentiation. We have here. We have this is the original function that we are interested in, and we want to find the derivative, right, or a description of how the slope is changing, of how this function is behaving over a series, right? So this is the k, and we take the k out. We kick the k out, and we say, okay, it's much more simpler to find the derivative of this x cubed. So then we differentiate the x cubed, which gives us obviously nx n minus 1. So it's 3 times 3 minus 1, which is 2. And then we go 10 times 3x squared is 30x squared. That's all that's being said here, right? So that's what is expressed here. Now let's talk about the second note for our power rule. So I'm gonna say a power rule 2, which is the following: the derivative of a constant term is 0. So can anyone here give me an example of a constant term? Just a constant term.
100.
100, right? So if y equals 100, what do we have? We have a straight line, right? And what's happening with the straight line? It's not changing. There's no change of y over x because it's horizontal or it's vertical. So y equals 100 or x equals 100 or x equals 0, whatever. Those lines, those straight lines do not have a slope. So there is no change of y over change x. So this rule, if we were to express this rule, this note, this subnote for the power rule, we can say the derivative of a constant term is 0. Or you can say, if we try to differentiate 5 or any constant, differentiate k, we will always get 0. And they have an example here where they try to find the derivative of 5, which is a constant term, 5, and they immediately give us 0. And then there's the third rule. And for to just expand our mathematical vocabulary a little bit here, because I mean we could describe the whole world using just words, but maths gives us a really good sort of utility for being more precise and describing the behavior of things, right? But then it's important that you first understand what we're talking about when we talk about a polynomial. Who here knows what a polynomial actually is? Because the third sub rule for the power rule kind of really hangs on you really understanding what a polynomial is. So can anyone here tell me what a polynomial actually is? Polynomial. So I'm gonna. Anyone know what a polynomial? We've been dealing with polynomials the whole of this last week. Oh, cool. So I'm gonna give you two mathematical functions, right? I'm gonna give you one function might be y equals f to the y equals 5, y equals x squared, like that, x squared. And then we have another function. So this is a example, function a, and then we might have another function. Put a little bit of space here. Function b, or another name for a function is a mathematical model to represent like a natural phenomena. We've obviously been dealing with phenomena in business because we're concerned with total costs and fixed costs and all these, and revenue and total revenue, etc. And then we have another model that I'm going to give you guys as an example, where fx equals the following, right? 5x to the power of 2 plus 2y minus 7. So now let's just zoom into both of these. So which one do you think is a polynomial in these two functions? Who wants to take a guess and explain why? Anybody at all? Notando. Now, why is function b a polynomial? Exactly. Exactly, right? A polynomial is a function that has a plus or a minus, that has more than one term that we're dealing with. And then if we're gonna do so, yeah, this is not a polynomial, even though it's an exponential function, which we are still interested in because we're dealing with non-linear functions, right, throughout the rest of the model. Even though this is a non-linear function, it's not a polynomial function. This is a polynomial function because we are dealing with multiple terms that are being added or subtracted to each other. Cool. So now let's go ahead and then describe, in terms of improving our mathematical vocabulary, give a definition for all of these terms within our polynomial. So who can tell me what the coefficients are in this function? What are the coefficients? Who wants to tell me? Who wants to take a guess? Okay, you're almost there. So 5 and 2 are the coefficients because we are timesing the 5 and the 2 by a variable. 7 is a constant, right? So this 5 and this 2, I'm gonna put here. So these two are the coefficients. Okay, this needs the text tool. So now, who can tell me what the operators are in this mathematical model? Anybody at all want to take a gamble? What are the operators?
Five, isn't it A, and then two B, and then seven, it's the constant, which is C.
So what are the operators in this mathematical model? So if you guys did the mathematical preliminaries or background is assumed to be in place section that's at the end of the book, you'd have known that an operator is anything is the these are the operators, right? There's a times here that we can't see, but it's an operator. This is an operator, and this is an operator. So these are the operators. So now who can tell me what the variables are in this function? Exactly. So variables, even in programming, if any of you are coders, variables are these buckets that we use to hold any value. We can kind of put any value that we want to use in these little buckets, and they help us to generalize a mathematical formula. So I'm just gonna put here variables or var. Okay, variables. I'm gonna write the whole thing up. Variables are y and x. And I always just think of them as buckets. Think of them as buckets that we can put anything into. Okay, cool. So now the third sort of note under the third kind of note under the power rule is the following, right? That the derivative of a polynomial function is the same as the derivative of its terms. So if you are trying to find, okay, so I'm gonna make a note here. The derivative of, and in more simple language, so the derivatives of the whole function is the same as the derivative of its individual individual terms. The derivative of the whole function is the same as the derivatives of, so we're only dealing with polynomials here. Polynomials is the same as the derivative of its individual terms. And then this is more tricky to explain via this kind of mathematical notation here. But what they're saying is here, if we have a multiple terms, if we're trying to find the derivatives of this whole series of terms that represents one mathematical model, we can actually split up all of the terms into individual terms and then find the derivative of each individual term, right? And then when we find the derivative of each individual terms, we then simplify it, and this new formula here is then the fx f is this here, f with the 1 at the top. So what I'm going to do is I'm just going to take a screenshot here, and I'm going to paste that screenshot over here. Cool. So we have an example that we've done here. Right. So now let's talk about, okay, we're running out of time. We only have 10 minutes. So let's talk about exponential and natural logarithms, right? Which was, if you go back to this little graph that we had here, is the second set of differential rules. No, that's not right. Differentiation rules. Okay, we can even call these derivative rules, to be honest. Differentiation rules. So, can anyone here tell me, is an exponential function, is it a polynomial or not? Anyone at all want to take a guess? I mean, you've all seen exponential functions when we dealt with hyperbolic, logistic, and exponential growth. How many terms does an exponential function have? An exponential function, okay, to answer my own question, an exponential function is not a polynomial, right? So what they're saying here is the derivative of an exponential function is the exponential function itself. So in English language, we can express this rule as the following. The derivative of a exponential function is the exponential function itself. And here they try to kind of throw us off by dealing with Euler's equation, right? So they give an example here where they say, dy over dx of any exponential function to the power of x. And just be very careful here, because when we are dealing with this rule, the exponent is the x and the base is a constant. Whereas when we were dealing with the power rule, the base was the x and the exponent was the term, the constant, sorry. So they're saying here, if we try to differentiate an exponential function, the result we get is the exponential function itself, like that. And then the exponential functions also has two kind of notes, right? We have this note, so I'm going to call this note 1. And then we also kind of have the second note that they give us here, which is to say that when an exponential function contains a constant, the derivative is the original exponential function multiplied by the constant. I have a mistake here. By the constant. I have a mistake here in my own notes. Can you believe it? Cool. So note two, in terms of exponential function, is the following, right? In words, if we were to describe this behavior in words, we can say that, when the exponential function contains a constant, the derivative is the original exponential function, and I'll put here not polynomial, because a polynomial and an exponential function are not the same thing. So it's the original exponential function multiplied by the constant. And then if we were to express this in terms of mathematical notation, we might say the following, right? If we were to differentiate the following function, so our original function might be the following, right? We might have y equals Euler's number to the power of, and in our power we have this behavior where we are timesing in our exponential function, right? So we might have ax as the power, as the exponent. Remember, this is still one term. So what they're saying here is, then if we were to differentiate this, dy divided by dx and then that, all we need to do is take this constant here and put it at the beginning of the function, and then that would be the original function's derivative. So in this example, we just take the original function like that, and we take this term. So when the exponential function contains a constant, so we take this constant and we just times it by the original function. So do you all understand that? Cool. I hope that's clear.
Yeah.
Cool. I can't afford to run over an hour tonight, but I think we're gonna have to continue with the. So we've done two rules and we've done the sub rule, and it seems to me that it's gonna take another hour for us to get through the rest of the section. So is it okay if we schedule that in for tomorrow, and then we just spend the last few minutes. I want some feedback. How are you guys finding this? Is there anything that I can improve? Would anybody like to lead tomorrow's session? Notando, you seem like you have something to say?
Well, I was trying to be very useful, but this is my first day attending.
Oh, okay. Interesting. It's your first day. Oh, okay. And have you gone through the content yet?
Yeah, I have.
Okay, cool. Anybody else have any feedback? Because the thing is, I'm getting all the learning now because I do the exercises on my own, and then I prepare for the lesson. And in the lesson, if I'm talking nonsense, you guys call me out. So I'm gonna get the best marks out of all of you. So is anybody else? So it'll be good for you guys to also take an opportunity to teach a session. And it's Halloween today, so for Halloween, I'm going to be dressed as a differential equation and scare all the children. So I'm off to my party now, and I'm going to go in as Euler's equation. Cool. So we'll do the chain rule and the product rule tomorrow. Otherwise, thanks everybody. And yeah, I don't think we'll get to higher derivatives. Do you guys want to maybe have a 1.5 hour session tomorrow instead of a 1 hour session? Alright, cool. So tomorrow then I'm going to start a little bit earlier at 6:30 to 8. Otherwise, everybody have a great evening, and please do the exercises and come with questions tomorrow. Cheers.
Thank you.
It's a pleasure. Bye.
Bye. Enjoy your party.
Halloween, yeah. Cheers. Bye.